Still working with our ABB resolver motor, but this time we are ready to do a final test. So again, from the minute screen here, our home screen on the software, final test, I'm going to go to motor and final test. I'm going to select my drop downs up here at the top, resolver, and again, the next two drop downs will default to generic and generic. The number of pole pairs of the motor that I'm working with, which is 4 pole pairs, and ABB 3HAC motor, 8 poles. And the next thing I'm going to do is connect to the drive. You can see the IP address for the drive shown on here, which should be the same as what is flashing on the front of your Runwell drive. And your Ethernet cable should be plugged into that X20 service port on the Runwell into the back of your Linea. So as long as that IP address is correct, you just click connect. And then we're going to program the drive with some certain motor parameters. Most of the time, these motor parameters are found on the nameplate, but if for any reason they're not there or you're not sure what the motor parameters are, please reach out to us. We'll be happy to help you. Also keep in mind there is a safety feature in place where you will not be able to enter a value higher than the drive output is rated for current or torque. So for this motor, we have 10 amps, 9.2 Newton meters, with a rated speed of 3,000 RPMs minimum. This motor does have a 24-volt brake, and you can see my lock-in value, V positive, W negative, has been pre-selected based on my drop downs up here. And then for my run parameters, the analytics time is the number of test minutes that are going to be used for the test. So I will use 6 of my test minutes to perform this final test. The runtime is not test minutes. That is only the amount of time that you want the motor to free run to get hot. So you can perform a check before when the motor is cold or at room temperature, and after when the motor has been running and is under stress. It's important to check both cold and hot. So that runtime is however long it takes to get the motor hot, usually 30, 60, maybe even 90 minutes, depending on the size of the motor. For this motor, normally I would let it run for about 60 minutes. In this case, I'm going to leave the runtime at 1 minute since this is just a demonstration. The speed at which the motor will run for that runtime, 1,000. And then your acceleration and deceleration speed, we'll just leave at 100. And once you have the parameters filled out, then we'll click Configure Drive. An extra step when dealing with resolvers, just like when we do alignments or lock-ins, is to verify the resolver parameters, 6 volts peak to peak and 5 kilohertz. And again, those values are defaulted because those are the 2 values that work with most resolver types. So you should not have to change these values, or very rarely have to change these values. So I'll just leave these at 6 volts and 5 kHz and click Confirm. And the final test mode, as with any run mode that deals with using the Runwell, the first thing that we do is hit clear faults. And before I click enable access, this is the point where I'm going to remind you to make sure that your motor power cable is plugged into the Runwell and to make sure that your motor is secured. Because once you hit enable access, you will be injecting current into the stator windings, which means that the rotor will find a naturally resting place, as that magnetism activates. So it is possible that the motor can jump when you hit enable access. Okay. You see that rotor did move. I have my motor secured, so we are good. And once the access is enabled, we can hit start collection. The first stage of the final test is a calibration procedure. This just verifies that the linea is detecting movement from the resolver based on the dropdowns that you've selected. And it is matching the angle count and the speed and the movement of the resolver with the RPMs that are assigned to the drive as the shaft moves. Because this is a closed loop system, it's important to make sure that the feedback is behaving the way that it's supposed to based on your feedback selections at the top, compared with how the actual motor is behaving as it's being driven by the drive here. Basically a synchronization procedure between the linea, the drive, and your feedback device. All right, so now that that calibration procedure is done, the system is reprogramming the drive to perform an alignment check based off that lock-in that we saw pre-selected in the setup page. So the system is expecting an electrical angle 0 at that V positive, W negative point. And because this is a full 4 pole pair motor, it is expecting to find that 0 at 4 different points throughout one mechanical rotation. So it is checking those 4 possible points. As you can see, it's looking at every possible lock-in angle on the found value, but it is only recording the one found at V positive, W negative as it goes around. And that should be the one that is closest to 0 if you're watching closely. So it'll check all 4 of those points. It'll check all 4 of those points several times to make sure that the feedback is properly aligned before moving on to the analytics portion of the final test, which does use the actual test minutes. So if my alignment is off, if it's misaligned, or I have something misconnected here, and it fails the commutation check, I'm not using any of my test minutes for the final test. I can go back and adjust my alignment and make sure that it's good, so I'm not wasting time. All right, so in this case, it did pass the first commutation check. And before moving on to analytics, we are just verifying amperage information from the stator windings. So it's recording the amperage pulled from each phase of the stator, U, V, and W, as reported from the drive. And what we're looking for here is symmetry, regular crossover, regular switching between U, V, and W. And this will be part of the report to give you an indication as to whether or not the stator itself and the motor is in good shape or not. This does not replace your safety checks. This does not replace, making sure that the phases are insulated from ground, not shorted to each other, things like that. All your safety checks that you do at your workbench are already done or should have already been done before you ever try to apply power to the stator. Okay. Okay, and now we are performing analytics on the resolver as we rotate the shaft here. And this is the part of the test that will use actual test minutes. As we saw before, it's 6 minutes in total. It's going to spend 3 minutes here in Analytics 1, and then it'll spend 3 minutes in Analytics 2 at the end of the free run cycle to check each individual channel of the resolver, reference, sine, and cosine, while the resolver is cold and while it is hot. So, and as this first minute completes, you'll see this minutes in use down here light up. It's performing a similar operation to what we did by hand in the analytics screen. Hopefully you've already watched that video. Except this time we're pulling data from the individual channels of the resolver at a constant rate of speed. And we're also taking into account the electronics and the magnetic fields and everything that's put off by the motor, rotor, and the stator, and the mechanics of the motor itself, which can affect the readings. And it's also worth mentioning that even though I don't have a signal display on this screen, the signal that's being analyzed is still being outputted to my oscilloscope. So I can't recommend enough that if you have an oscilloscope that you like to use, please use those breakout leads on the back of the linea so you can view the signals in real time on your scope. All right, it has now completed the first round of analytics. So this is the free run period. This is, like I said, what I would normally run for about 60 minutes or so, long enough for the motor to get hot. And during this free run time, this is when I would check for any mechanical issues in the motor. Listen for bearing noise, listen for any kind of brake noise or brake drag, anything like that. Any kind of abnormal vibration from the motor. Just anything mechanical is what you would catch during the free run period. Again, for the purposes of this demonstration, it's only going to run at 1,000 RPMs for about a minute. Just like that. And then after the free run time, we are essentially going to repeat the steps that we performed at the beginning of the test, including the calibration procedure, just to make sure that everything is still in sync, nothing got knocked loose or anything like that during the free run time. Okay, it's completed the second calibration phase. So now the Linea is reprogramming the drive to do a second commutation check. That's the alignment check to make sure that our alignment is still good. And this will verify that, the resolver didn't come loose while it was running for an hour. Maybe I didn't have my set screws tight enough, something like that. Or maybe the core, maybe the screw that holds the core in place onto the rotor wasn't tight. So just making very sure that that alignment is still good. All right. Still in good shape on the alignment. So now we are at the final stage of the final test here, which is our second analytics phase. Once again, the system is checking each channel for a solid minute, pulling many more samples than we did in the analytics hand test. And now presumably the resolver has been under heat stress because we've been running the motor for an hour. So we can see if there's been any kind of degradation in the signal, any, either the sine or cosine channel going out, or just giving bad signal strengths, anything like that. It is very important to check your feedback device, not only when it's cold, but also while it's hot and has been under heat stress and under the kind of conditions that it would be in with the motor actually, running. If you're familiar with resolvers, they're designed to be pretty rugged and pretty durable, and to be able to withstand harsher environments than, say, your normal encoder. But it is still important to check. And as you can see down here, We've already used 2 minutes, so we're on to our third. So our final test should be almost complete. Just like that. So once the final test completes, a report pop up like we saw or we would see for analytics will happen again, and you can fill out your customer information, job ID, work order ID, however you track your work, who performed the test, the resolver serial number or part number, and your motor ID or serial number, motor manufacturer, and then any additional information. Rebuilt motor, final test, all that good stuff. And then once those fields are filled out, click Save and Show. And there's our final report. So the final report looks similar to the analytics report. However, there are some key differences. Again, here's the information that we populated at the top, along with the company logo, which again, should be your logo. If you haven't sent us a high resolution picture to have your logo loaded onto here, please do. And here's our data summary. Overall condition of the resolver, in this case, of the feedback device is excellent. Additional information not included in the analytics report is that it did pass our commutation test or the alignment check. As you can see down here in the summary, the expected values versus the found values. And this shows about 99% compared to when we performed analytics, and it was only 89%. All right. So on the graphical display, here are the data points that were collected, particularly for the sine channel. And you can see having the resolver attached to an actual moving rotor and stator, and the electromagnetics involved with that actually pulled the signal strength of the sine and probably the cosine. Yep, up a little bit since we did the analytics one. If you watch the analytics video for this. So no voltage errors, no variance or noise, a little bit of distortion blips, but that is completely normal in low doses when running an actual motor. And then an additional graph for the final test. That only shows up for the final test report is this right here. This is the report of the amperage test that we performed before the first analytics check, where we actually checked the phase windings, the UVW windings of the stator itself. So you can see UVW, the amplitude for all three are right about the same. And you can see switching at regular intervals. And all the waveforms look approximately similar. So I would say that this stator is even in good shape. And then we can view the individual data points. You can even see where our distortion faults occurred. And I will say it's interesting that both for sine and cosine, those distortion faults are happening at about 70 electrical degrees. seems to be only in that one point. So I am still completely confident that this resolver is good. I'm very curious to what's going on at that particular point. So something worth investigating. But still, overall, this encoder is considered, or I'm sorry, this resolver is considered excellent. Not a problem. My motor's been rebuilt. I know the alignment's good. I know the resolver is good. And I am ready to send this particular motor out the door. Thank you very much for your time. And we are always available to help. Just shoot us an email at support@octavaengineering.com. And I thank you very much for your time.